Chapter 4. The heat of the cook, evaporation, pressure, and the physics of failure. There's a quiet lie that television tells whenever it shows chemistry in action. It's the idea that heat is simple. Turn the flame up, speed things along, and everything behaves exactly as planned. In Breaking Bad, heat is treated like a tool, something Walter White controls effortlessly, something that bends to his will, something that never truly fights back. But in the real world, heat is not obedient. Heat is chaotic. It spreads unevenly. It builds pressure invisibly. It accelerates reactions beyond control, and it turns minor mistakes into catastrophic failures. And nowhere is this disconnect between fiction and physics more apparent than in the way Breaking Bad portrays cooking environments, evaporation, and pressure dynamics. Let's start with the most fundamental issue: open systems versus closed systems. In real chemistry, the distinction between these two determines whether a reaction proceeds calmly or becomes lethal. An open system allows gases to escape. Pressure remains near atmospheric levels. A closed system traps vapor, increasing internal pressure with every degree of added heat. Many of the setups shown in Breaking Bad exist in an uncomfortable middle ground, sealed enough to trap pressure, but improvised enough to lack pressure relief mechanisms. This is a nightmare scenario for any chemist, because pressure does not announce itself. It does not hiss politely. It builds silently until the weakest point in the system fails, and when it does, the release is violent. In the RV lab, for example, reactions are often heated aggressively on improvised burners. Containers are sealed or partially sealed. Tubing is inconsistent. Valves are crude or non-existent. In reality, this environment would be a pressure accident waiting to happen. Solvents like ether, methanol, acetone, and toluene have low boiling points. As temperature rises, they vaporize rapidly. Vapor occupies far more volume than liquid. Trapped vapor increases pressure exponentially. Even a few degrees above boiling can multiply internal pressure beyond the tolerance of glassware, plastic tubing, or makeshift seals. In professional labs, pressure-rated vessels, reflux condensers, and pressure relief valves exist precisely to prevent this. Walt's setups have none of these safeguards. The show frequently depicts Walt speeding things up by adding heat. This is a common Hollywood trope, but in real chemistry, increasing temperature doesn't just make reactions faster, it changes them. Reaction pathways shift. Side reactions become dominant. Thermal decomposition begins. Solvents break down. Intermediates destabilize. What was once a clean synthesis becomes a chemical soup of unwanted byproducts. The idea that Walt can simply crank up the heat without consequence ignores the delicate balance that governs real reactions. Many reactions require narrow temperature windows. Too low and nothing happens. Too high and everything goes wrong. Walt's apparent immunity to these constraints is pure fiction. Then there's evaporation, one of the most misunderstood processes in the series. Evaporation is not just liquid turning into gas. It is governed by surface area, airflow, vapor pressure, temperature, and ambient humidity. In Breaking Bad, solvents evaporate cleanly and completely in open rooms, leaving behind pristine crystals. In reality, uncontrolled evaporation is one of the fastest ways to contaminate a product. Airborne dust settles into solutions. Moisture from the air dissolves back into hygroscopic compounds. Solvents evaporate unevenly, trapping impurities within the crystal lattice. Residual solvent pockets form, lowering purity and stability. Real chemists use rotary evaporators, vacuum chambers, desiccators, and inert atmospheres to manage evaporation precisely. Walt often uses none of these. Even more dangerous is thermal runaway, a phenomenon the show never acknowledges. Some reactions generate heat as they proceed. If that heat is not dissipated, it accelerates the reaction further, producing even more heat. This feedback loop can escalate rapidly, turning a stable reaction into an explosion or fireball. Industrial disasters have occurred for exactly this reason. Walt's reactions, especially scaled-up batches, would be highly vulnerable to runaway conditions. Yet the show portrays large-volume reactions proceeding calmly under intense heat, as if thermodynamics simply takes the day off. Pressure buildup is another silent killer ignored for narrative convenience. In one scene, Walt and Jesse cook inside confined spaces with poor ventilation. Vapors accumulate. Flammable atmospheres form. In reality, a single spark from static electricity, faulty wiring, or a hot surface could ignite the entire space. Many illicit labs are discovered not by police work, but by explosions. Firefighters responding to house fires often uncover labs that detonated due to vapor ignition. Breaking Bad largely avoids this outcome because the story requires the lab to survive. But physics would not be so forgiving. The superlab, despite its professional appearance, also suffers from unrealistic portrayals of heat management. Industrial-scale reactions generate enormous thermal loads. They require cooling jackets, heat exchanges, circulation systems, and constant monitoring. The show depicts Walt managing massive batches with little more than vigilance and experience. In reality, even small miscalculations could warp vessels, degrade products, or trigger emergency shutdowns. Gus's lab would require an entire team of engineers to operate safely. Instead, it runs flawlessly with minimal oversight. Another example of narrative convenience overriding physical law. And then there's the human factor. Heat affects people, not just chemicals. High-temperature environments increase fatigue, reduce concentration, and amplify errors. Working in respirators, protective suits, or confined spaces further degrades performance. Walt and Jesse often cook under extreme stress, emotional conflict, sleep deprivation, and physical danger. In real labs, these conditions are a recipe for disaster. Mistakes compound, timings slip, measurements drift, reactions fail. The show portrays Walt as immune to these limitations, as if intellect alone shields him from human vulnerability. But no chemist, no matter how brilliant, escapes biology. What Breaking Bad ultimately presents is a fantasy of control, a world where heat obeys intention. Pressure remains tame, evaporation behaves politely, and reactions reward confidence. Real chemistry is the opposite. It punishes arrogance. It exposes shortcuts. It magnifies small errors into large consequences. Heat is not a servant. It is a wild force that must be respected, contained, and constantly monitored. Walt's success depends not on realistic thermodynamics, but on the suspension of them. And this brings us to the deeper theme of the series, hubris. Walt believes he can control everything, his chemistry, his circumstances, his destiny. The show allows him this illusion far longer than reality would. In the real world, heat and pressure would be the first to humble him. They would not care about his intellect, his pride, or his plans. They would do what physics always does, follow the laws, not the story. Pressure without warning. How real labs fail in seconds. One of the most dangerous illusions Breaking Bad creates is the idea that pressure is obvious, that you can see it coming, hear it building, sense it before disaster strikes. In reality, pressure is a silent predator. It accumulates invisibly, obeying simple gas laws that care nothing for intention or intelligence. Boyle's law, Charles's law, the ideal gas equation, these are not abstract formulas from textbooks. They are the invisible hands tightening around any closed or semi-closed system exposed to heat. And the labs depicted in Breaking Bad are full of systems that would, in reality, be flirting constantly with catastrophic failure. Every time Walt heats a sealed or partially sealed container, pressure begins to rise immediately. Even liquids that appear calm can be producing vapor beneath the surface. Solvents with low boiling points generate gas rapidly, and when that gas has nowhere to go, it increases internal pressure exponentially. This is not a gradual cinematic buildup. There is no dramatic warning hiss. There is only a critical threshold, and once it is crossed, the container fails violently. Glass shatters, seals rupture, contents aerosolize, flames ignite. The show routinely ignores this reality, depicting reactions proceeding calmly even when every physical condition suggests imminent rupture. Consider the use of improvised tubing and connectors, rubber hoses, plastic fittings, makeshift clamps. These materials are not pressure-rated. They deform under heat. They weaken chemically when exposed to solvents. They lose elasticity. Microcracks form. In real laboratories, pressure-rated tubing is selected based on chemical compatibility, temperature tolerance, and maximum pressure limits. In Breaking Bad, pressure containment is treated as an afterthought. And yet, nothing fails. Nothing ruptures. Nothing leaks. Physics politely steps aside so the story can continue. Then there is the issue of gas generation during reactions. Many chemical reactions release gases as byproducts. Hydrogen, carbon dioxide, ammonia, sulfur dioxide expands rapidly when heated. In closed systems, these gases dramatically increase pressure. In open systems, they displace oxygen, creating asphyxiation or explosion risks. The show rarely acknowledges gas evolution, and when it does, it treats it as a nuisance rather than a lethal hazard. In reality, uncontrolled gas release is one of the most common causes of lab accidents. Entire buildings have been destroyed because a reaction generated more gas than the system could vent. The RV lab is particularly egregious in this regard. A confined space, poor ventilation, heat sources, flammable vapors, and improvised seals create the perfect storm for pressure-related disasters. In the real world, such a setup would be statistically destined to explode or suffocate its occupants. Even opening a door too quickly could introduce oxygen into a vapor-rich environment and cause ignition. The fact that Walt and Jesse cook repeatedly in this environment without triggering a single pressure-induced catastrophe is not realism, it's narrative mercy. And pressure doesn't just threaten explosions, it distorts reactions themselves. Increased pressure changes boiling points, alters equilibrium positions, and affects reaction rates. A reaction designed for atmospheric pressure can behave unpredictably under elevated pressure. Products may polymerize. Side reactions may dominate. Desired outcomes may vanish entirely. Walt's ability to maintain perfect reaction control while ignoring pressure dynamics defies not just physics, but basic chemical engineering. The Superlab introduces another unrealistic assumption. That scale does not change pressure risk. In reality, scaling up magnifies pressure problems exponentially. Larger volumes trap more vapor. Heat dissipates more slowly. Pressure gradients form within vessels. Hot spots develop. Industrial reactors require extensive pressure monitoring systems, emergency vents, rupture discs, and automated shutdown protocols. Gus's lab, as depicted, operates with minimal visible safety infrastructure. Walt relies on experience and observation, not sensors and safeguards. In the real world, this approach would end in disaster long before perfection. Another overlooked factor is pressure cycling. Heating and cooling systems repeatedly causes materials to expand and contract. Over time, this fatigues seals, weakens joints, and creates hidden failure points. Real labs track equipment lifespans and replace components proactively. Walt's setups are reused endlessly without degradation. Glassware doesn't weaken. Tubing doesn't crack. Valves don't fail. The show ignores the cumulative toll that pressure cycles take on real equipment. And then there's the human cost. Pressure accidents are rarely survivable. They do not injure politely. They maim, blind, burn, and kill. Shrapnel travels faster than reaction time. Vaporized chemicals penetrate lungs instantly. Skin contact becomes catastrophic when substances are aerosolized under pressure. Real chemists treat pressure with deep respect because they know how unforgiving it is. Walt, however, treats pressure as something he can outthink, and the show allows him that illusion until pressure manifests metaphorically in his personal life instead. This is the deeper irony of Breaking Bad. The show externalizes pressure psychologically rather than physically. Walt's world becomes more intense, more volatile, more dangerous, but the chemistry remains obedient. In reality, chemistry would have been the first thing to turn on him. Pressure would have been the silent antagonist long before rival cartels or law enforcement appeared. It would have punished his shortcuts. It would have exposed his overconfidence. It would not have waited for dramatic timing. Pressure does not care about genius. It does not respect narrative arcs. It follows laws written into the fabric of the universe. And every time Breaking Bad shows a heated, sealed container surviving against all odds, it is quietly asking physics for permission. Physics politely declines, but the story proceeds anyway. Evaporation isn't magic. Why solvents don't simply disappear. One of the most persistent misconceptions reinforced by Breaking Bad is the idea that evaporation is clean, obedient, and final. Heat a liquid, wait a moment, and it vanishes, leaving behind only what you wanted. It's an idea so intuitive that it feels true, and yet it is deeply misleading. In real chemistry, evaporation is one of the messiest, most contamination-prone stages of any synthesis. It's where impurities concentrate, where environmental exposure peaks, and where products are most vulnerable to irreversible damage. The show treats evaporation like a cosmetic step. Reality treats it like a critical bottleneck. Evaporation is governed by vapor pressure, temperature, airflow, surface area, and ambient humidity. Change any one of these variables, and the retanned outcome changes. In Breaking Bad, solvents evaporate evenly and completely in open rooms, regardless of conditions. In reality, open-air evaporation invites chaos. Air currents cause uneven cooling. Moisture from the atmosphere dissolves back into hygroscopic compounds. Dust, fibers, pollen, and microscopic debris settle into exposed solutions. The longer a solution sits open, the more contaminated it becomes. This is why professional labs avoid open evaporation whenever possible. They use vacuum systems, rotary evaporators, and inert gas blankets to control every variable. Walt often uses none of these, yet achieves flawless results. Another overlooked reality is residual solvent retention. Even when a liquid appears dry, solvent molecules can remain trapped within the crystal lattice. These invisible pockets reduce purity, alter melting points, and affect stability. Forensic labs detect these residues easily. They are among the most common impurities found in real-world samples. In the show, however, crystals emerge from evaporation pristine and complete, as if solvents obey an unspoken agreement to leave no trace. That is not chemistry. That is wish fulfillment. The problem worsens with scale. Large volumes evaporate unevenly. Outer layers dry first, trapping solvent inside. Heat gradients form. Crystallization begins prematurely, locking impurities in place. Real chemists mitigate this with slow, controlled evaporation or vacuum-assisted removal. Walt often accelerates evaporation with heat guns or open flames, methods that would almost guarantee uneven drying and contamination. Yet his crystals are always perfect, always stable, always ready for distribution. Humidity is another silent enemy the show ignores. Many chemical compounds readily absorb water from the air. This moisture alters crystal structure, promotes decomposition, and reduces shelf life. In uncontrolled environments like basements, RVS, and underground labs, humidity fluctuates constantly. Professional labs monitor and regulate humidity precisely. Walt's environments would be a nightmare for moisture control, and yet water never interferes. Crystals never clump. Products never degrade. Again, physics politely steps aside. Evaporation also affects safety. As solvents evaporate, they fill the surrounding air with flammable vapors. Without proper ventilation, these vapors accumulate, creating explosive atmospheres. In real life, Many lab accidents occur during solvent removal, not during synthesis. A single spark can ignite an invisible cloud. In Breaking Bad, evaporation is visually dramatic but physically harmless. Vapors never ignite unless the story demands it. This selective danger undermines the reality of how perilous evaporation truly is. There's also the issue of selective evaporation. Not all solvents evaporate at the same rate. Mixtures separate unevenly. Some components linger longer, altering concentration ratios. This changes reaction outcomes and product composition. Walt's mixtures behave as if all solvents evaporate uniformly, leaving behind exactly what he intends. In reality, evaporation reshapes the chemical landscape unpredictably, unless tightly controlled. The show's portrayal of evaporation reinforces a larger myth, that chemistry is forgiving, that mistakes can be erased with heat, that impurities vanish if you wait long enough. In reality, evaporation magnifies mistakes. It concentrates impurities. It exposes products to the environment. It demands patience and control. Walt's impatience, his constant push to speed things up, would sabotage real chemistry at this stage more than any other. Yet again, the show substitutes symbolism for accuracy. Evaporation becomes a metaphor for transformation, impurities burning away, essence remaining. It's elegant storytelling, but it's not science. Real evaporation doesn't purify. It reveals. It exposes everything that went wrong earlier in the process. And in Walt's chaotic, improvised setups, evaporation would be the moment when flaws become impossible to hide. What Breaking Bad gives us is a fantasy where solvents obey intention, where air remains clean, where moisture stays away, and where evaporation is merely a transition. Real chemistry offers no such courtesy. It demands respect, control, and humility. It punishes shortcuts ruthlessly. And in the real world, Walt's reliance on uncontrolled evaporation would be one of the first cracks in his myth of perfection. Evaporation isn't magic. Why solvents don't simply disappear. One of the most persistent misconceptions reinforced by Breaking Bad is the idea that evaporation is clean, obedient, and final. Heat a liquid, wait a moment, and it vanishes, leaving behind only what you wanted. It's an idea so intuitive that it feels true, and yet it is deeply misleading. In real chemistry, evaporation is one of the messiest, most contamination-prone stages of any synthesis. It's where impurities concentrate, where environmental exposure peaks, and where products are most vulnerable to irreversible damage. The show treats evaporation like a cosmetic step. Reality treats it like a critical bottleneck. Evaporation is governed by vapor pressure, temperature, airflow, surface area, and ambient humidity. Change any one of these variables, and the rate and outcome changes. In Breaking Bad, solvents evaporate evenly and completely in open rooms, regardless of conditions. In reality, open-air evaporation invites chaos. Air currents cause uneven cooling. Moisture from the atmosphere dissolves back into hygroscopic compounds. Dust, fibers, pollen, and microscopic debris settle into exposed solutions. The longer a solution sits open, the more contaminated it becomes. This is why professional labs avoid open evaporation whenever possible. They use vacuum systems, rotary evaporators, and inert gas blankets to control every variable. Walt often uses none of these, yet achieves flawless results. Another overlooked reality is residual solvent retention. Even when a liquid appears dry, solvent molecules can remain trapped within the crystal lattice. These invisible pockets reduce purity, alter melting points, and affect stability. Forensic labs detect these residues easily. They are among the most common impurities found in real-world samples. In the show, however, crystals emerge from evaporation pristine and complete, as if solvents obey an unspoken agreement to leave no trace. That is not chemistry. That is wish fulfillment. The problem worsens with scale. Large volumes evaporate unevenly. Outer layers dry first, trapping solvent inside. Heat gradients form. Crystallization begins prematurely, locking impurities in place. Real chemists mitigate this with slow, controlled evaporation or vacuum-assisted removal. Walt often accelerates evaporation with heat guns or open flames, methods that would almost guarantee uneven drying and contamination. Yet his crystals are always perfect, always stable, always ready for distribution. Humidity is another silent enemy the show ignores. Many chemical compounds readily absorb water from the air. This moisture alters crystal structure, promotes decomposition, and reduces shelf life. In uncontrolled environments like basements, RVS, and underground labs, humidity fluctuates constantly. Professional labs monitor and regulate humidity precisely. Walt's environments would be a nightmare for moisture control, and yet water never interferes. Crystals never clump. Products never degrade. Again, physics politely steps aside. Evaporation also affects safety. As solvents evaporate, they fill the surrounding air with flammable vapors. Without proper ventilation, these vapors accumulate, creating explosive atmospheres. In real life, many lab accidents occur during solvent removal, not during synthesis. A single spark can ignite an invisible cloud. In Breaking Bad, evaporation is visually dramatic but physically harmless. Vapors never ignite unless the story demands it. This selective danger undermines the reality of how perilous evaporation truly is. There's also the issue of selective evaporation. Not all solvents evaporate at the same rate. Mixtures separate unevenly. Some components linger longer, altering concentration ratios. This changes reaction outcomes and product composition. Walt's mixtures behave as if all solvents evaporate uniformly, leaving behind exactly what he intends. In reality, evaporation reshapes the chemical landscape unpredictably, unless tightly controlled. The show's portrayal of evaporation reinforces a larger myth, that chemistry is forgiving, that mistakes can be erased with heat, that impurities vanish if you wait long enough. In reality, evaporation magnifies mistakes. It concentrates impurities. It exposes products to the environment. It demands patience and control. Walt's impatience, his constant push to speed things up, would sabotage real chemistry at this stage more than any other. Yet again, the show substitutes symbolism for accuracy. Evaporation becomes a metaphor for transformation, impurities burning away, essence remaining. It's elegant storytelling, but it's not science. Real evaporation doesn't purify. It reveals. It exposes everything that went wrong earlier in the process. And in Walt's chaotic, improvised setups, evaporation would be the moment when flaws become impossible to hide. What Breaking Bad gives us is a fantasy where solvents obey intention, where air remains clean, where moisture stays away, and where evaporation is merely a transition. Real chemistry offers no such courtesy. It demands respect, control, and humility. It punishes shortcuts ruthlessly, and in the real world, Walt's reliance on uncontrolled evaporation would be one of the first cracks in his myth of perfection. When reactions go wrong, temperature errors, and chemical chaos, chemistry does not fail loudly at first. It fails quietly, subtly, and invisibly, especially when temperature is mishandled. One of the most misleading ideas reinforced by Breaking Bad is that reactions either work or explode, with nothing in between. In reality, the most dangerous failures are the ones that look successful on the surface but are chemically ruined underneath. A reaction can appear complete while producing the wrong compound, unstable intermediates, or toxic byproducts. Temperature errors are the most common cause of this silent failure, and the show treats them as inconsequential. Every chemical reaction has an optimal temperature range. Outside that range, reaction rates change, equilibrium shifts, and competing pathways activate. Too cold, and the reaction stalls, leaving unreacted precursors. Too hot, and the molecules gain enough energy to form side products, decompose, or rearrange into unintended structures. In real labs, temperature is monitored constantly. Even a few degrees matter. Walt, however, often works with crude heating methods, open flames, improvised burners, hot plates with poor regulation. These tools lack precision. Temperature fluctuates wildly. Hot spots form, yet the reactions never suffer. Chemistry bends to narrative convenience. One of the most dangerous temperature-related phenomena is thermal decomposition. Many compounds break down when overheated, producing toxic gases or unstable residues. This doesn't require extreme temperatures, sometimes just a slight overshoot is enough. Decomposition products can contaminate the final material irreversibly. No amount of purification can remove them completely. In the show, Walt routinely pushes reactions aggressively, yet decomposition never occurs unless the plot demands tension. In reality, decomposition would be a constant threat. Temperature also affects reaction selectivity. Molecules can follow multiple reaction pathways depending on thermal conditions. A perfectly controlled temperature favors the desired product. A poorly controlled one opens the door to everything else. This is especially true in multi-step syntheses, where early-stage errors propagate through the entire process. Walt's ability to achieve perfect outcomes while ignoring this complexity is one of the show's most unrealistic elements. Then there's the issue of heat transfer. Large reaction vessels do not heat evenly. The outer edges warm faster than the center. Without proper stirring and thermal regulation, gradients form. These gradients cause different parts of the mixture to experience different chemical conditions simultaneously. Industrial reactors use jackets, coils, and circulation systems to manage this. Walt's setups rely on manual stirring and intuition. In reality, this would produce inconsistent products at best and dangerous runaway reactions at worst. Temperature mistakes also compound over time. A single overheated step can damage catalysts, degrade solvents, or alter intermediates in ways that affect every subsequent stage. The show portrays chemistry as forgiving mistakes can be corrected later. Real chemistry is not so kind. Once a reaction path is altered, the damage is often permanent. Walt's chemistry seems immune to this cascading effect. The show also ignores the relationship between temperature and pressure. Heating increases vapor pressure, which increases internal pressure in sealed systems. Temperature errors don't just ruin reactions, they create physical danger. Overheating can turn a stable setup into an explosive one. Walt frequently pushes temperature boundaries without triggering pressure failures. This is another example of physics being suspended for storytelling. Perhaps the most unrealistic element is Walt's reliance on instinct. He feels when a reaction is right. He adjusts heat based on intuition. While experience does matter in chemistry, it is never a substitute for instrumentation. Real chemists trust thermocouples, digital readouts, and feedback systems, not gut feeling. Walt's success without precise temperature control turns chemistry into a mystical art rather than a measurable science. This portrayal feeds into the myth of the lone genius, the idea that brilliance transcends rules. But chemistry does not reward brilliance alone. It rewards discipline. It rewards caution. It punishes arrogance. Walt's approach would work once, maybe twice by chance. Sustained perfection under such conditions is fantasy. What Breaking Bad ultimately does is shift the consequences of temperature mismanagement away from chemistry and into narrative drama. Instead of reactions failing, relationships fail. Instead of products degrading, people betray one another. The chaos exists, but it's emotional, not chemical. In reality, the chemistry would collapse long before the personal drama escalated. Temperature is not a backdrop. It is a controlling force. Ignore it, and chemistry turns hostile. Respect it, and reactions behave. Walt's world ignores this balance, allowing him to defy thermodynamics in service of storytelling. But in the real world, temperature errors would be his undoing long before the empire crumbled. The breaking point. Why DIY labs collapse under real physics. By the time Breaking Bad reaches its most intense moments, the audience has been conditioned to accept a dangerous illusion that chemistry, no matter how improvised, will keep working as long as Walter White is in control. The RV lab survives heat, pressure, evaporation, contamination, and human error. The super lab operates flawlessly despite scale and complexity. Time and again, physics is pushed to the edge and politely steps back. But in the real world, this is where everything collapses. DIY labs do not fail slowly. They fail suddenly, violently, and without mercy. The fundamental problem is that improvised setups lack redundancy. Professional labs are designed around failure. They assume something will go wrong, and they build in safeguards to prevent catastrophe. Pressure relief valves, automatic shutoffs, fire suppression systems, secondary containment, continuous monitoring. DIY labs have none of these. When a mistake occurs, and it always does, there is nothing to catch it. In Breaking Bad, mistakes become dramatic turning points. In reality, they become explosions, fires, or chemical exposures that end the operation permanently. One of the most overlooked issues is cumulative error. Each step in a chemical process introduces small deviations. Impurities, temperature fluctuations, solvent residues, measurement inaccuracies, all of these stack. Over time, the system drifts further from ideal conditions. Professional labs recalibrate constantly to prevent this drift. Walt never recalibrates. His glassware never warps. His instruments never drift. His measurements remain perfect indefinitely. This is not realism, it's mythology. DIY labs also struggle with waste management. Every reaction produces byproducts. Spent solvents, contaminated materials, residues that must be neutralized or disposed of safely. In Breaking Bad, waste disappears conveniently. In reality, waste accumulates, creating additional hazards. Stored waste can react unexpectedly, release gases, or ignite. Many real-world lab accidents occur not during synthesis, but during cleanup and storage. Walt's labs never face this reckoning. Another breaking point is ventilation. Proper airflow is essential to prevent vapor buildup, manage heat, and protect human health. DIY labs rarely have adequate ventilation. The RV, basements, and underground spaces shown in the series would trap fumes, deplete oxygen, and concentrate toxins. Prolonged exposure would cause dizziness, cognitive impairment, and long-term damage. Walt and Jesse remain sharp, focused, and physically capable under conditions that would debilitate real people. Biology, like physics, is suspended. Fire risk is the final and most unforgiving reality. Flammable solvents, ignition sources, and confined spaces form an explosive combination. In real life, meth labs are frequently discovered because they burn down. Fires are not rare accidents, they are statistically inevitable outcomes of poor control. Breaking Bad avoids this fate because the story demands continuity, but physics would not cooperate. The sheer number of ignition opportunities shown would guarantee disaster. The show also ignores the psychological toll of constant danger. Real chemists working in high-risk environments experience fatigue, stress, and decision paralysis. Errors increase, judgment degrades. Walt, however, becomes sharper under pressure. Stress enhances his performance. This inversion of human behavior serves the narrative, but contradicts reality. Pressure breaks systems. It doesn't perfect them. In the end, Breaking Bad presents a fantasy where control triumphs over chaos. But chemistry is chaos constrained by rules. Remove the rules and chaos wins. DIY labs do not sustain empires. They collapse under the weight of physics, chemistry, and human limitation. Walt's survival is not proof of genius, it's proof of storytelling. And this is the core truth of Chapter 4. Heat, pressure, evaporation, and temperature are not obstacles to be overcome by brilliance. They are fundamental forces that demand respect. Ignore them, and no amount of intelligence will save you. Walt's world allows him to defy these forces until the narrative is ready to punish him. Reality would not wait. The illusion of control. Why physics always collects its debt. By the end of Breaking Bad, it becomes clear that the greatest fiction the show ever told was not about drugs, or explosions, or blue crystals. It was the fiction of control. Walter White believes that if he understands a system deeply enough, he can dominate it. Chemistry becomes his proof, his sanctuary, his weapon, his identity. Heat obeys him. Pressure stays silent. Evaporation behaves. Temperature errors forgive themselves. But in the real world, physics does not grant second chances. It keeps accounts. And eventually, it collects. Every process we've examined in this chapter, heating, evaporation, pressure management, temperature control, exists on a knife's edge. These are not background details. They're the forces that decide whether a reaction proceeds safely or becomes catastrophic. Professional laboratories exist because these forces are unforgiving. They are why chemists wear protective gear, why systems are monitored obsessively, why redundancy is non-negotiable. Walt's success depends on bypassing all of this. He succeeds not because his methods are sound, but because the story protects him from consequences until it no longer can. This illusion of control mirrors Walt's personal arc perfectly. Early on, his chemistry seems to validate his belief that mastery equals safety. Each successful cook reinforces the idea that he can outthink danger. But this belief is the same flaw that ultimately destroys him. Just as he underestimates people, he underestimates physics. He treats systems as obedient when they are merely patient. In reality, heat does not care who you are. Pressure does not respect intelligence. Evaporation does not pause for ego. Temperature errors do not negotiate. They wait, and then they act. The reason real illicit labs fail is not because the people involved are foolish. It's because the environment is hostile. Chemistry is demanding. Physics is relentless. Human beings are fallible. The show removes these constraints to explore a different kind of truth, one about pride, power, and identity. But it does so by bending the physical world into something symbolic rather than accurate. And it's not a flaw in storytelling. It's a choice. And understanding that choice allows us to appreciate the show without confusing it for reality. What Breaking Bad gets right is the emotional truth of science, the obsession, the intimacy, the sense of creation. What it gets wrong is the mechanical truth, the relentless consequences of physical law. In real life, Walt's lab would not be a stage for genius. It would be a countdown timer. Every cook would increase the probability of failure. Every shortcut would compound risk. The empire would end not with gunfire or betrayal, but with a flash, a rupture, or a silent leak that no one saw coming. And that is the final lesson of Chapter 4. Physics does not dramatize its revenge. It doesn't wait for symbolism. It doesn't care about arcs. It simply acts when conditions demand it. The only reason Walt survives as long as he does is because Breaking Bad chooses to make physics a supporting character instead of the antagonist it truly is. In the next chapter, we move beyond the slow, invisible dangers of heat and pressure, and into the moments where Hollywood spectacle collides directly with physical reality. Explosions, fires, shockwaves, detonations. We'll examine what really happens when energy is released violently, and why the show's most dramatic moments are also its most scientifically revealing. Chapter 5. The Chemistry of Explosions and Fires. Beyond Hollywood. Explosions are the language of television drama. They are loud, immediate, and emotionally decisive. When something explodes on screen, the story tells us that a line has been crossed and there is no going back. Breaking Bad uses explosions sparingly but strategically, turning moments of chemical violence into symbols of power, intimidation, and consequence. But real explosions are not symbols. They're physical events governed by strict laws of energy, pressure, and reaction kinetics. And when you examine the show's most famous explosive moments through the lens of real physics, a very different story emerges, one where danger is less theatrical but far more lethal. The first misconception the show reinforces is that explosions are interchangeable. Fireballs, shock waves, concussive blasts, and rapid burns are all treated as variations of the same phenomenon. In reality, they are fundamentally different processes. Combustion, deflagration, and detonation are not interchangeable terms. Combustion is a controlled chemical reaction that releases heat and light over time. Deflagration is a rapid burn that travels slower than the speed of sound. Detonation is a shock-driven reaction that propagates faster than sound, producing extreme pressure and destructive force. Breaking Bad often blurs these distinctions, allowing explosions to behave however the scene requires. This blurring is especially evident in how fires are depicted. Fires in the show ignite instantly, spread predictably, and burn cleanly. Real fires are chaotic. They depend on fuel availability, oxygen concentration, temperature, and containment. Many chemical fires produce toxic smoke, invisible gases, and unpredictable flame behavior. Some burn almost invisibly, others explode only after a delay. The show simplifies these dynamics for clarity, but in doing so, it removes the true danger of chemical fires, their unpredictability. One of the most iconic explosive moments in the series involves intimidation rather than destruction, the fulminated mercury scene. The explosion is dramatic, loud, and controlled. But even before we analyze that specific compound, it's important to understand a basic truth. Real explosions are rarely survivable at close range. Shock waves travel faster than human reaction time. Pressure damages organs before pain is felt. Shrapnel becomes the primary killer. The show allows characters to stand feet away from explosive events and walk away shaken but intact. Physics would not be so merciful. The environment also matters. Explosions behave very differently indoors versus outdoors. Confined spaces amplify pressure, reflect shock waves, and increase lethality. Many scenes in Breaking Bad involve explosions or fires in enclosed environments, rooms, vehicles, buildings. Yet the damage remains localized and controlled. In reality, confinement dramatically increases destructive potential. Walls become shrapnel. Pressure rebounds. Oxygen depletion suffocates survivors. The show downplays these effects to keep characters alive. Then there's the matter of ignition sources. Fires and explosions require specific conditions to occur. Fuel, oxygen, and ignition must align. Breaking Bad often skips these prerequisites, allowing explosions to occur on cue. In reality, many attempted ignitions fail, smolder, or burn unevenly. Others ignite unexpectedly long after the triggering event. The show compresses time and probability into certainty. Chemistry becomes obedient to narrative timing. Another major misconception is scale. Small amounts of energetic material produce limited effects. Large explosions require large amounts of energy. The show sometimes portrays small quantities producing outsized results. This exaggeration serves drama, but distorts reality. Energy cannot be created from symbolism. It must come from mass, chemical bonds, and reaction speed. When the show violates this principle, it enters pure fantasy territory. Perhaps the most misleading element is survivability. Characters are exposed to heat, pressure, and shock that would cause severe injury or death in real life. Burns would be deeper. Hearing loss would be permanent. Internal injuries would be catastrophic. The show minimizes these consequences to maintain momentum. Physics is again subordinated to storytelling. But despite these inaccuracies, Breaking Bad does capture something important: the psychological power of explosions. They represent loss of control, a sudden release of energy that cannot be negotiated with. And that metaphor aligns beautifully with Walt's journey. Explosions in the show are not accidents, they are statements. They announce that chemistry is crossed into violence. In the next parts of this chapter, we'll examine these explosive moments one by one, what they would really look like, how they would behave under real physics, and why Hollywood chooses spectacle over accuracy. Because when chemistry turns violent, the difference between fiction and reality becomes impossible to ignore. Fulminated mercury, bang, whimper, or something in between. Few moments in Breaking Bad are as instantly recognizable as the fulminated mercury scene. Walter White walks into Tuco Salamanca's office carrying what appears to be a bag of crystal meth. tension hangs thick in the air. A single crystal is thrown to the ground and the room erupts in a blinding explosion. Glass shatters. Walls shake. Tuco is stunned. Walt stands unharmed, triumphant. It's a masterclass in intimidation. It is also one of the most misunderstood portrayals of explosive chemistry in television history. Fulminated mercury is real. It is highly unstable. And it is dangerous. But it is not a magical super explosive that behaves like a Hollywood grenade. Chemically known as mercury-2 fulminate, it is a primary explosive, meaning it is sensitive to shock, friction, and heat. Historically, it was used in percussion caps and detonators, not as a bulk explosive. Its purpose was to initiate other, more powerful explosives. On its own, its explosive power is limited. It deflagrates rapidly rather than detonating with the sustained shockwave depicted in the show. The explosion shown in Breaking Bad is visually closer to a high explosive detonation than a fulminate reaction. The pressure wave is strong enough to shatter windows and knock people off balance, yet localized enough to avoid killing anyone in the room. This balance is convenient for storytelling, but physically implausible. Real fulminated mercury would produce a sharp, violent reaction, but on the scale of the amount shown, it would be unlikely to create a room-filling shockwave without catastrophic injury to those nearby, including Walt himself. There's also the issue of quantity. The bag Walt carries appears to contain several grams, possibly more. That amount of fulminated mercury would be extremely dangerous to handle. Even slight movement could trigger detonation. Carrying it loosely in a bag, tossing it casually, and striking it intentionally would be suicidal. Real chemists handle primary explosives in milligram quantities, using specialized tools and remote manipulation. The show portrays Walt handling fulminated mercury with bare hands, calmly and confidently, as if it were stable. It is not. Then there's the matter of containment. When fulminated mercury reacts, it does not produce a controlled explosion. It fragments violently, projecting hot debris and mercury compounds in all directions. These fragments would become shrapnel, causing severe injuries. Mercury vapor and toxic residues would contaminate the room. The show depicts a clean blast with minimal debris and no toxic aftermath. This sanitization removes the true danger of such an event. The environment of the explosion also matters. Tuco's office is a confined indoor space. Explosions indoors are far more destructive than those outdoors. Pressure waves reflect off walls, amplifying their effect. Glass becomes high-speed shrapnel. The fact that characters remain conscious and largely unharmed contradicts what physics predicts. At that distance, ear damage alone would be inevitable. Internal injuries would be likely. Walt's survival, standing feet from the blast, stretches plausibility beyond its limit. Another critical misconception is the idea of selective force. The explosion damages the environment dramatically but spares the people conveniently. Real explosions do not discriminate. Energy disperses according to physics, not narrative importance. If the blast were strong enough to shatter windows and collapse structural elements, it would be strong enough to cause serious harm to anyone nearby. The show decouples environmental damage from human injury to preserve characters. Despite these inaccuracies, the scene succeeds because it communicates power. Walt uses chemistry not to destroy, but to dominate psychologically. The explosion is less about energy and more about fear. And in that sense, the science becomes symbolic. Fulminated mercury is chosen not for realism but for mystique. It sounds dangerous. It feels unpredictable. It reinforces Walt's transformation into someone who commands forces others don't understand. But the real lesson of the scene is not about explosive chemistry. It's about how Hollywood reshapes reality to fit narrative needs. Fulminated mercury is dangerous, but not in the way the show portrays. Its true danger lies in its unpredictability, not its raw power. And that unpredictability is precisely what the show suppresses. Because real explosions are messy. They injure indiscriminately. They don't leave room for monologues or triumph. In the real world, Walt's stunt would likely have ended his story instantly. Not with applause, but with emergency sirens. Not with intimidation, but with irreversible consequences. The fact that it doesn't tells us everything we need to know about how Breaking Bad treats explosive chemistry as a narrative tool, not a physical reality. Fire, flash, and fallout. Why TV flames lie. Fire in television is treated as a visual event, bright, loud, dramatic, and strangely clean. In Breaking Bad, flames erupt when they need to, burn with cinematic intensity, and then conveniently subside. They rarely choke rooms with smoke. They rarely poison the air. They rarely behave unpredictably. But real fires are not performances. They're chemical chain reactions governed by fuel availability, oxygen concentration, and heat feedback loops. And when you examine the fires in Breaking Bad through this lens, you begin to see how deeply Hollywood sanitizes one of nature's most violent processes. At its core, fire is rapid oxidation. Fuel molecules react with oxygen, releasing heat, light, and combustion products. But what those products are and how fast they formed depends entirely on conditions. Many chemical fires do not produce dramatic flames at all. Some burn nearly invisibly. Others generate thick, toxic smoke that incapacitates before heat becomes dangerous. In Breaking Bad, fires are almost always visually legible. You can see them. You can run from them. This alone places the show firmly in fiction. Consider the types of fuels involved in the series. Solvents like ether, acetone, methanol, and toluene are extremely flammable. Their vapors ignite far more easily than their liquids. In confined spaces, vapor clouds form explosive mixtures with air. A single spark can cause a flash fire and instantaneous ignition that engulfs a room in flame. These fires often last only seconds, but they are lethal. In Breaking Bad, such vapor ignitions rarely occur unless the plot demands spectacle. In reality, they would be a constant threat. Another major omission is smoke toxicity. Chemical fires produce a cocktail of gases: carbon monoxide, nitrogen oxides, hydrogen cyanide, sulfur compounds, and partially burned hydrocarbons. Many of these gases are colorless and odorless. They incapacitate quickly. Most fire-related deaths are caused by smoke inhalation, not burns. Characters in Breaking Bad often remain conscious and functional in smoky environments far longer than physiology allows. This again reflects narrative priority over realism. Heat behavior is also misrepresented. Fire does not spread evenly. It follows airflow. It climbs. It creates thermal layers. In enclosed spaces, temperatures near the ceiling can exceed survivable limits within seconds, while the floor remains deceptively cooler. Professional firefighters train to read these gradients because misjudging them is fatal. The show depicts characters standing upright in burning rooms, moving freely, and escaping with minor injuries. Real fires would incapacitate them almost immediately. Flashover is another phenomenon the show ignores. When a room fills with superheated gases, everything ignites simultaneously. This is not gradual. It is sudden and unsurvivable. Many of the environments shown in Breaking Bad rooms filled with flammable materials. Poor ventilation, high heat would be prime candidates for flashover. Yet it never occurs, because flashover leaves no survivors and no room for dialogue. There's also the myth of controlled ignition. Characters ignite fires deliberately, expecting predictable outcomes. In reality, fires rarely obey intention. Ignition points spread unpredictably. Secondary ignitions occur. Structures collapse. Fuel sources shift. The idea that one can use fire as a precise tool without extensive planning and safeguards is a Hollywood fantasy. Then there's the aftermath. Fires don't end cleanly. They leave toxic residues, structural damage, lingering heat, and compromised air quality. Buildings affected by chemical fires are often uninhabitable without extensive remediation. Breaking Bad frequently treats fires as isolated events, dramatic but contained. The long-term consequences vanish between scenes. Once again, the show prioritizes metaphor over mechanics. Fire represents chaos, loss, escalation. It marks turning points in the story, and in that role it is effective. But the price of that effectiveness is realism. Real fire is not cinematic. It is fast, suffocating, and lethal in ways that do not translate well to television. The deeper truth is this: if Breaking Bad depicted fire accurately, the story would end abruptly. Characters would not survive repeated exposure to flammable environments. Labs would burn down early. Empires would collapse before they formed. Fire would not be a dramatic punctuation, it would be a full stop. And so the show lies, not maliciously, but deliberately. It reshapes fire into something manageable, readable, survivable. Real fire is none of those things. It is indifferent. It does not care about narrative pacing or character development. It reacts according to chemistry, and chemistry does not negotiate. Pressure, shock waves, and the myth of contained destruction. One of the most persistent myths reinforced by Breaking Bad is the idea that energy can be released violently yet remain conveniently contained. Explosions shake rooms without collapsing them. Shock waves shatter glass without rupturing organs. Pressure bursts outward just enough to impress, but not enough to kill. This illusion is essential to the show's pacing, but it directly contradicts how pressure behaves in the real world. Pressure does not respect narrative boundaries. It expands until it dissipates or destroys whatever confines it. When an explosion occurs, energy is released faster than the surrounding air can move out of the way. This creates a shock wave, a sudden spike in pressure that travels outward at supersonic speed. This wave does not slow down because characters need to survive. It does not weaken selectively. It compresses air, ruptures eardrums, collapses lungs, and transfers force into solid structures. In confined environments, this wave reflects, overlaps, and intensifies. The more enclosed the space, the more destructive the effect. Many of the explosive moments in Breaking Bad occur indoors or in partially enclosed spaces. Physics predicts that such settings would amplify damage dramatically. Pressure would rebound off walls, creating multiple shock fronts. Windows would not merely shatter, they would become high-velocity projectiles. Walls would crack or fail. People would not be knocked backward dramatically. They would suffer internal injuries before they even realized what happened. The show replaces these outcomes with cinematic motion slow reactions, ringing ears, stunned expressions, because true pressure injuries are invisible and inconvenient for storytelling. Another misconception is the idea that shock waves push people away. In reality, blast injuries often involve a rapid overpressure followed by a sudden vacuum. This pressure differential can tear tissue, rupture blood vessels, and cause brain injury without external signs. Characters in the show are thrown backward, bruised but conscious. Real victims would likely collapse where they stand, disoriented, injured, or dead. The body is not designed to handle rapid pressure changes, no matter how resilient the character. The show also treats structural integrity as static. Buildings absorb explosions without meaningful consequences. In reality, repeated pressure events weaken materials. Microfractures form. Load-bearing elements fail. A structure exposed to even a single significant blast may be unsafe afterward. The idea that characters can return to damaged environments without concern reflects another layer of simplification. Physics accumulates consequences. It does not reset between scenes. Then there's the myth of precise energy release. Explosions in Breaking Bad are portrayed as targeted tools, damage here, intimidation there, no collateral effects beyond what the plot requires. Real explosions are indiscriminate. Energy spreads spherically unless constrained, and constraints increase danger rather than control it. The fantasy of a just enough explosion is a narrative convenience, not a physical possibility. Pressure also interacts with heat. Explosions generate extreme temperatures, even if only briefly. These temperatures can ignite secondary fires, weaken metals, and damage infrastructure. The show often separates explosions from fires as if they were distinct events. In reality, they're often inseparable. A blast may be over in milliseconds, but the thermal damage continues long afterward. Another overlooked factor is sound. Explosions produce sound levels far beyond safe limits. Permanent hearing loss would be inevitable for anyone nearby, yet characters recover their hearing quickly, if at all. This again reflects a preference for visible drama over invisible injury. Sound damage is real, lasting, and cumulative, but it doesn't read well on camera. What Breaking Bad ultimately presents is a world where energy behaves politely. It announces itself. It damages surfaces more than bodies. It leaves protagonists standing. This is not how physics works. Energy is blind. It flows according to gradients and constraints, not intentions. If the show respected real pressure dynamics, many scenes would become impossible to stage. Characters would be incapacitated too quickly. Environments would become uninhabitable. The story would grind to a halt under the weight of consequences. And so pressure, like fire and explosives, is tamed. It becomes a visual effect rather than a physical force. Don't forget to like, share, and subscribe for more.